Hi, I'm Nerea, and this is my poster about synthesis of magnetic cobalt ferrite nanoparticles by the colloidal method using the surfactant ethyl bumethylamine-benzyl sulfate. In recent years, there has been growing interest in the development of nanomaterials due to their potential application in fields such as medicine, biotechnology, electrochemistry, and the food industry. The latter field of is of particular interest due to the high regeneration of waste from food decomposition caused by microorganisms. Among the various types of nanomaterials, magnetic nanoparticles have attracted greater interest for their potential to increase the shelf life of foods. These particles can be synthesized from iron, cobalt, or mixtures of both. With sizes ranging from 1 to 100 nanometers, they can be obtained by various methods, such as particle crushing, top-down, atom-by-atom assembly bottom-up, or homogeneous nucleation in the liquid phase, followed by chemical and physical treatment. The latter, the latter method generates high restrictions as the synthesis conditions allow control over the size and shape of the magnetic nanoparticles. This work this work presents the results obtained through the synthesis of cobalt ferrite magnetic nanoparticles using the colloidal method assisted by microwave and ultrasound in the presence of the surfactant 3-methyl ammonium bromide. The objective of this work is to synthesize cobalt ferrite nanoparticles using the colloidal method and engage to microwave or an ultrasound with water and ethanol as solvents and cetri-trimethyl ammonium bromide as the surfactant to control particle morphology and size. The presence of cobalt ferrite was confined by UV spectroscopy, and the structural characteristics were analyzed using FTIR, XRT, and SAM. Additionally, microbiological tests were conducted on 4 different media. The methodology of the nanoparticles were synthesized using a colloidal method, which include the following steps. First, aqueous aqueous solution of cobalt and iron salts in a 1 to 2 molar ratio was prepared, to which the surfactant was added. The mixture was subjected to ultrasound to ensure homogeneous dispersion, and then heated by microwave to promote nanoparticle formation. After heating, the solution was dried at 200 degrees Celsius and then calcinated at 600 degrees Celsius, resulting in a black powder of cobalt ferrite. Then we have the results of the FTIR spectra that show characteristic vibrational modes of cobalt ferrites with distinctive signals at 579 and 462. The UV spectrum shows a characteristic signal around 550 nanometers, confirming the presence of cobalt ferrite. Then the X-ray diffraction patterns show peaks corresponding to cobalt ferrite at approximately 18.3 degrees, 30.1 degrees, 35.5 degrees, and others, confirming the crystalline structure of the synthesized material. Then we have scanning electron microscopy and transmission electron microscopy. The, that we obtain the scanning electron microscopy reveals the surface morphology of the nanoparticles, showing agglomeration of cobalt ferrite particles. Transmission electron microscopy confirms that the particles are smaller than 100 nanometers. Finally, the microbiological test showed that cobalt ferrite nanoparticles inhibit the growth of various microorganisms, suggesting their potential use in the food industry for food preservation. And for conclusion, magnetic cobalt ferrite nanoparticles were obtained using a colloidal method assisted by microwave and ultrasound. XRD results confirm the presence of cobalt ferrite, although iron oxide was detected as a byproduct. Some and microorganisms show particles in the nanometer range, and FTIR and UV-Vis spectroscopies confirm the presence of cobalt and Co and Phi oxides. Finally, microbiological tests determine the inhibitory capacity against certain microorganisms. And that will be all for me. Thank you very much for your attention and your interest in my poster.